Yeah. Continuing today the lectures on deep learning, and Gitta is going to present a very interesting application area where these concepts can be used. Interest on.
Yes.
Probably related to imaging.
Okay, yeah. Welcome back. So I hope my voice is a bit better today. So let's see how things work. Yeah, as Wolfgang already said, I mean, this will be now about applications of deep learning in, let's say, mathematical methodologies. Yesterday we talked about the theory of deep learning. So what we saw was, I mean, there are basically 4 areas where I think very interesting questions of deep learning come up. The area of expressivity, then learning, generalization, and also this area of explainability. But also at the same time, you see that deep learning also infuses a lot of mathematical methodologies like inverse problems. And so this will be the focus of the lecture today. So I think in general, I already said last time, we are living in very interesting times. So in this, let's say, middle of models and data. So maybe let's make this a bit more precise. And we saw also in this, I think, spring school, a lot of very interesting applications of mathematical modeling, simulation, optimization. Here are also a couple of those. Design of, for instance, airplane wings and so on, where these methods have tremendous impact. But there are also a lot of other examples. So, for instance, if you want to discern turbines concerning noise, minimal noise emission, if you are interested in molecular dynamics on the atomistic level, then you, for instance, face problems like that only at very large timescales interesting events happen, and so this with just traditional modeling was not possible to actually simulate accurately so that you can capture these interesting events. Also, if you go in the direction of astrophysics, if you look at star formation, where usually a lot of turbulences happen, there, I mean, modeling that accurately is also just, let's say, pure PDE models, currently not possible. So therefore, there's a need to go, let's say, a bit beyond and also take data into account. Then on the other hand, and we already saw this slide, there's this whole area now of data science, deep learning in particular, where you have very powerful models and methods. Sorry, very, very powerful methods. But as I said, there are very few theoretical foundations which in a way support that side. So I think, therefore, we are living in this, let's say, century where on the one hand you have all these, let's say, very well understood methods of mathematical modeling, building PDEs, depending on physical insight, simulation, optimization. On the other hand, forgetting everything, just using, for instance, deep learning, data-based methods on acquired data sets. And so the question is how to deal with this and how to combine those in some way. And so there are a lot of approaches how to combine, let's say, both worlds. So if you start on the left-hand side, there are certainly these pure data-driven approaches. You have, I mean, millions of data. You just train your neural network, forget everything about physics, which you know, and aim then to detect maybe some structural components in the data set. Then if you want to invoke physics, maybe a bit more, there is this stream of machine learning where you would like to bring in physical constraints, maybe in the neural network in some way, so inserting physical information in that. Then going maybe a bit more to the other side, let's say parametric PDEs, where you aim to learn the parameters depending on your given data set. So there you have already a bit more physical structure, data assimilation, and then maybe on the far side where you have, let's say, PDEs which drive your simulation, and then the simulated data you then afterwards analyze with machine learning algorithms. So, and I think this is also as we know, the main theme of the spring school. On the one hand, you have, let's say, model-based methods. On the other hand, you have data-based methods. So the question is how to bring this together. And in some sense, in an optimal way, whatever optimal means. Yeah, so I mean, what we will do here is we want to drive, let's say, the classical methods as far as they go, and then use deep learning just for the part which we cannot handle otherwise. And so I think from my perspective, since these machine learning and deep learning methods are not that well understood yet, this is in some sense the best way to handle this. Good. So this is what I plan to do today. As Wolfgang already said, we look at inverse problems, in particular from the area of imaging sciences. We first need to learn a bit about what people have been done so far, solving inverse problems. So there are methods like Tikhonov regularization, Sparse regularization. So this, we will see what has been done there and what the, let's say, classical methods are to solve those inverse problems in imaging sciences so far. Then we go in the direction of deep learning. And we will see, first of all, that these methods, in particular one particular application, reach a boundary which, I mean, people worked on for a long time to get beyond that, but could not. So that there are indeed problems where here you reach a boundary. Then we will discuss what deep learning, how people use deep learning so far in inverse problems. Give a bit of overview how this is, let's say, incorporated so far. And then we will look at this problem of limited angle computed tomography, where we will discuss one approach, which is in some sense a hybrid approach that, as I said, you use classical methods as far as they go. And then only for that which you cannot do otherwise, you just use deep learning just specifically for that, which is in some sense learning only the invisible, which other methods cannot see. So that's the plan. Okay. Yeah, so I myself also come from the area of imaging sciences and inverse problems. I think it's a very exciting area. There are now a lot of methods which acquire data like CT, scanners, electron tomography, and so on. And also a lot of those problems then can be phrased in terms of inverse problems. So for instance, if you would like to, just in the easiest case, you acquire an image which is affected by noise, you would like to denoise this image, or you acquire an image but you don't acquire all parts of it, you're missing certain parts. Also that is an inverse problem. So an inverse problem, we will see it on the next slide. You have an operator, a forward operator, for instance, which affects an image with noise, and you would like to invert this operator. So that's what an inverse problem in general terms is. But also, I mean, let's say all these data acquisition techniques are typically also inverse problems. You have a forward operator which acquires the data. You don't get the data, let's say, in terms of an image, and then you need to invert it to get to your image. Now we will see that. Okay, so what is an inverse problem? You have a forward operator k, so this can go from, let's say, one Hilbert space to another. It can also be, let's say, x and y are Hilbert spaces. You have a forward operator, you know k, your operator, you know y, what you acquired, the data you acquired, and you would like to recover x. Yeah, so as I said, k could be something which just adds noise to the image, so you get the noisy image, you would like to get x back. Or it could be something which punches a hole in your x, you get this, so the image with the hole, and then you would like to fill the hole, so which is typically called in-painting. But it could be also something else. It could be, for instance, for magnetic resonance imaging, where typically you acquire an image by just computing point samples of the Fourier transform. So then these would be the point samples of the Fourier transform of your image, and you would like to recover your true image. Or K could be the radon transform, which it will be later on, and then you would like to invert it. So often you face a situation that you have an ill-posed inverse problem. So there are notions of well-posedness. For instance, that for each y you get a unique x. Also that x depends continuously on y, but typically these inverse problems are not well-posed. So for instance, think of this, as I said, inverse problem where you have, let's say, a k. In the easiest case, you have an operator k which takes an image and then basically takes out the middle part. Certainly, I mean, if you would like to recover your initial image, this is not unique. I mean, you can fill in whatever you like. So this would be a severely ill-posed problem, also affecting with noise and so on. All of those are what's typically called ill-posed problems. And so there are various ways to solve this. One is, and one very popular, is what's called Tikhonov regularization. So what is Tikhonov regularization? What you do is you look at this functional and you minimize it. So let's take a look at what this does. If you minimize this functional, you see you have this term. Now if you minimize this term over x, this means you would like to enforce that you solve this inverse problem as accurately as possible. So that's the so-called data fidelity term. But it could be, as we saw there, that there are infinitely many solutions for that. I mean, you can fill in this hole whatever you want. So what you also need to incorporate is some prior knowledge on the data, on the image you would like to recover. And so this prior knowledge you now put into what's called the regularization term. So in the easiest case, in the standard Tikhonov regularization, you would just like to recover that x which has the smallest norm. But this might not always be the best. But I mean, this is in a way one classical approach. So you want to solve your inverse problem as accurate as possible. This is then what you put in as additional knowledge about the image you would like to recover. This alpha is the so-called regularization parameter. It balances between those two terms. So it tells what is more important to me. Is it more important for me to solve this as accurately as possible, or is the prior knowledge more important to me? And so if this is, let's say, very large, then it would put a lot of pressure on this. If it would be very small, it would put a lot of pressure on this to minimize this part. Good. So now, I mean, as I guess we all know or can imagine, this might not be the best just minimizing the norm of the image. So there, I mean, if I would do that, I would just fill this hole with zeros, which might not be great. So therefore, people generalize this and just incorporated here just a very general penalty term or regularization term. And so now the question is, and there's a whole zoo of different terms you can fill in here. You would like that certainly in the end the solution depends continuously on the data, and you would like to incorporate some properties of the solution. And there's a whole, let's say, zoo of how you can choose this P. I mean, everybody has a favorite, let's say it's his or her favorite term, also depending on which application you work on. One very popular choice is the last choice, which is called Sparse Regularization. And so this is what we will look at now. So what is the philosophy there if you follow this, let's say, strategy? So remember, I mean, this is now what we want to put in as prior knowledge on our image, in this case, which we want to recover. So the philosophy there is that all images which we have in real life are somehow compressible. So we can always find a transform which in a way brings out just the information content, and this information content is then very small. So very popular is what is called the wavelet transform, and also there wavelets already appeared in Ron's talk. So a wavelet, basic terms, is a system, a wavelet system, which basically looks like this. You have a generator function, then you have this J is a zooming parameter, and this M is a translation parameter. So wavelets in 2D look, for instance, like this. So you can zoom into the signal, and you can also move them around. And so the transform then is to take an image and map it to these inner products of the image with these wavelets, which basically then the coefficients tell you to which extent this wavelet is contained in the image. This is also the basis for this compression standard JPEG 2000. And so you see this here, this is an image, this is the wavelet transform, so each point here which you see corresponds to one of these inner products. And so what you observe is that many of those areas are black. There the coefficients are very small or equal to 0. So and this JPEG 2000 compression standard just discards all those black parts and just saves these white parts. And so you see these white parts the number of pixels are much smaller than the image itself. So this in a way reveals, let's say, roughly speaking, the information content of this image. So this is the philosophy. There's always, for each class of data, you can always find a sparsifying transform. And so this goes into the direction of dictionary learning. Already Ron talked about dictionaries. So there are algorithms which, if you have a given class of data, for which you can learn a representation system which sparsifies this data. Yeah, so what is sparsifying actually? So there are two philosophies one can look at. Let's say 2 viewpoints. So what you want to do is, if you have a class of, let's say, data in some Hilbert space, you have a system. You can either look, as we did for the decay, at the decay of the coefficients. Yeah, so you would like that this sequence, as n goes to infinity, has rapid decay. Or you can look at, some sense, approximation properties. You can look at the error of best n-term approximation. Yeah, so this we already saw, I think, in Ron's talk, error, and then also in my talk yesterday. So you take your data, you approximate it by n terms of your representation system. You do it in a way that this is minimized, and then you let n go to infinity, and again you look at the decay. Now, the question is, are those viewpoints the same or not? Well, if you have an orthonormal basis, these are the same, but typically, also in imaging sciences, we do not take orthonormal basis in this, often not orthonormal basis in this case. So we go to redundant systems, so-called frames, and then these viewpoints are actually not the same. So one has to be a bit careful what one talks about there. So this also goes in the direction of compressed sensing, which I'm sure a lot of people might have already heard of. The compressed sensing problem is also an inverse problem, finite dimensional inverse problem. Just a linear system of equations like this, which I guess also maybe in Calculus 1 you already studied. Only here you have a highly underdetermined matrix, so a very flat and long matrix, so that you have infinitely many solutions x. And again, the question is, I would like to recover x. And so what I do here is also following this philosophy that there is always a representation system which sparsifies my data. And so I solve this problem also in this way. So this is then also comparable to the, let's say, regularization term which we saw before. Now, why is this L1 norm that interesting? Just, let's say, heuristically. So what happens if you want to solve this? So let's assume the x I would like to recover. Let's say this is in R2. And let's say all x's, all solutions of this problem lie on this line. Just for the sake of explanation. And now I would like to recover the sparsest of those. So now I could minimize, sorry. So let's assume these inner products, these inner products, I just have 2 lambdas, these inner products are, give me this line. Yeah, and now I would like to solve, I would like to take the sparsest of those. Now how do I get the sparsest of these elements in this line? Well, I could solve the L2 norm. Yeah, I could minimize the L2 norm. So what do I do if I minimize the L2 norm? I take the L2 ball, I blow it up, and at some point it will hit this line. Yeah, and so at that point where it will hit the line, that's this point on the line which has the smallest L2 norm. And that will be somewhere here in this case. But then I can also take the L1 norm. The L1 norm is this diamond. So I blow up the L1 norm, it hit this line, and then it hit it here. Now this solution has 1 non-zero entry and 1 zero entry. This has 2 non-zero entries. So this is definitely sparser. So therefore this L1 norm promotes sparsity. Yeah, so in some sense, intuitively, this L1 norm pushes the solutions towards the axis. And so therefore, the L1 norm is always taken when you know that what you would like to recover is sparse. I mean, certainly it would be much better to take the L0 norm, or maybe an LP norm for p less than 1. But here you have a convex problem to solve, and so this you can do in a fast way. Good, and so there are also a lot of other earlier footprints in this direction, inverse problems, which I don't want to talk about too much. I mean, maybe just, I think, also one breakthrough paper by these three authors is where, in inverse problems, I think for one of the first times, there is a general theory for sparse regularization. So I think this. And here also we have Ron, who also has, I think, you see this is even an earlier version where also sparsity already appears. Okay, good. So I think, yeah, so you get the slide so you can see then and check out these three papers. And also compressed sensing appeared in two different, let's say, papers. One paper by Candace Romberg and Tao, and then also by Dave Donahoe and Parrott. Good, so we end up with this functional which we want to minimize. So again, recall this was the data fidelity term. This is the penalty term, and here we now choose the L1 norm of a certain coefficient sequence where hopefully we can choose these elements of a representation system so that this is sparse. Either it has just very few non-zero entries, or it at least has rapid decay, this coefficient. Okay. Now, choosing these psi lambdas, I mean, there are a lot of choices. Again, delving into this area of applied harmonic analysis, or computational harmonic analysis, or modern harmonic analysis, how people call it sometimes these days, so there are a lot of choices. All those are typically designed in such a way that these are multi-scale systems. They are usually designed in the Fourier domain. That's where this harmonic analysis part come in. Certainly you would like that this sequence can be rapidly computed, and you would like to have some sort of optimality condition. Okay, so this is this philosophy of sparse regularization. So using a penalty term where you penalize if your recovered image is not sparse in the representation system you aim for. Good, so now also for later on, we want to use a specific representation system, which are shearlets. They already appeared briefly in the talk yesterday. And the philosophy there is that images are typically governed by edge-like structures, and this is what we want to now use as a prior information on the image we aim to recover. So in images which we'll look at later on for computed tomography, you see these edges are quite prominent. In other images as well, but also in natural images, if you just have the edge information, typically you already know very well what the image shows you. This was taken by Dave Donahoe and phrased into a model for images. So this is in some sense also, so if you talk about models, I think you also have to be very careful what you mean by that. So the model could be the data acquisition process itself, or it could also be the model for the image. So the model for the data you want to recover. So if you talk about model, every, let's say, community has maybe also different viewpoints, so one has to be careful what, if you say just in general models, what you actually mean by this. So in this case, in our talk, the acquisition process will be clear, but what we will focus on for model will be always the model for the data we aim to recover. Good. So here he introduced what he called the class of cartoon-like functions. So maybe let's just draw a picture. So these just look like this. So you have a function defined on the unit square. You have a distinctive discontinuity curve. You have inside. So inside you have the function f1 plus f2, and outside you have the function f1. And so this area here is the area B. Okay. Good. So this is maybe a kind of rough but useful class for functions which are governed by anisotropic features, namely this discontinuity curve. So then the question is how to design systems which actually approximate this in an optimal way or sparsify it in an optimal way. Now, if you have curve structures, and you saw before that these wavelets are kind of isotropic, they don't have a specific direction. They are not anisotropic, and also there actually Ron already talked about that. So these are isotropic objects. You need much more to approximate this structure than if you have anisotropic elements. Yeah? So if you now look at these inner products, certainly here many more of the inner products of your data with wavelets are large than if you would have elements which look like this, already visually somehow. And so now to design functions which have this shape, one takes a particular scaling matrix which gives an anisotropic scaling. And so these objects which you design that way have a length of 2 to minus j half and a width of 2 to j. So if you let j go to 0, they become very needle-like. In contrast to wavelets, you now also need an operation to change the direction, which is done by shearing because it's consistent with the digital grid. So I mean, shearing applied to the digital grid leaves it invariant, so you have a faithful implementation in the end. And that leads to what one calls a sheared system. So you see, if you look here, you have a generator. You again have a translation, so you move these things on the plane. You have the scaling, so you can zoom in. And you have the shearing, so you can change the orientation. And why does it look so complicated? Well, what you want to do is you want to partition the frequency of Fourier domain. So if you look at the Fourier transform of these, of the low frequency parts, the essential support is in here. If you look at the frequency support of these functions, they lie, let's say, in here, in this cone and in this cone, and this is responsible for this cone. Yeah. So in that sense, this system tiles the frequency domain in this way. Yeah, is this somehow clear? So if you take the Fourier transform of these functions, essentially they are supported in these little tiles. And also on this side. And then this is just switched by 90 degrees. And so these different areas here correspond to the j. So j is the scale. So j as the scale goes to infinity. First you take elements in here, then in here, and so on. Okay. Good. And so what does it have to do with these cartoon-like functions? You can show that if you take an element of the cartoon-like functions, you take shearlets. Now remember, we had these two viewpoints of sparsity. We had this viewpoint where we look at the decay of the coefficient sequence, and we had this viewpoint where we looked at the error of best n-term approximation. So the decay of the coefficient sequence can be bounded in this way. The error of best n-term approximation in this way. In both cases, this coefficient as well as this exponent as well as this exponent are the optimal possible. You cannot go beyond that. So up to these log factors, this is optimal in both cases. So both, if you just are interested in the decay of the coefficient sequence as well as the error of best n-term approximation. And this is important here because that's not an orthonormal basis. So that's a so-called frame. It's a redundant system. So these viewpoints are not the same.
When you say they are optimal, you mean they are optimal for this sheared system, or for you say that any frame for this class cannot be better than this?
They are optimal for cartoon-like functions. So there's a result by Dave Donohoe where he shows that if you have any system which is kind of reasonable, I mean, any representation system which is, so there's this notion of polynomially bounded, but I mean any system which is, let's say, for instance, not dense in L2, R2, and you want to approximate cartoon-like functions, then this n to the minus 2 is the best possible, and also this. Yeah. Okay, and then, I mean, you can use it for this in-painting, which you actually have here. So this is, I think, an interesting application. It comes from seismology. So you have the top of the Earth here. This is the time axis, and so seismologists are interested in detecting the underground structure of the Earth. So what they do is, at some point, they have an explosion, initiate an explosion, or have a vibrator truck. And so these waves enter the ground, and then they are scattered. And they place sensors on here. And so with time, I mean, these sensors record some scattered waves. But since you cannot place sensors everywhere, you have these black strips in those areas. And so then, I mean, from an image like this, they want to recover the structure underneath these black strips, so the missing data. And so with this technique, which we discussed before, so sparse regularization. Maybe let's go back so that we see it again. So now, this is this in-painting. So this operator which punches holes, these black strips in the image, and now we take shearlets. And then if you minimize this and solve this, then this is what you get. So kind of accurately you can fill in these missing parts. Now, if you're interested, you want to try it yourself. We have a webpage, shearlab.org, and no matter which language you speak, we, I think, basically have them all. So we have it in MATLAB, Julia, Python, and also TensorFlow. I mean, so there's a shearlet package and also different demos. So for instance, the in-painting one and so on. So you can play around there. It's in 2D and 3D and also parallelizable. Okay, so this was so this was about sparse regularization. So now we saw inverse problems, and shearlets, sparse regularization with shearlets are a very good way to solve inverse problems in imaging, because they give you good prior information on the image you want to recover. Okay, so now mathematical modeling, and remember what I mean by model. In this talk, it will be the model for the data you want to recover. Good, so we go to computed tomography. You are all very young. I guess you haven't experienced lying in such a CT machine. I mean, people use it in hospitals to detect, in some sense, the structure of bodies and the damage to a human body. So we will see it in a bit more mathematical detail in a moment. Let's just look at it as a rough level. So you have here the body. So what it does, it computes line integrals in one direction, and then it sweeps around the body. So in each time, if you compute these line integrals, you get one slice of what's later on called the sinogram. So the acquired data looks like this. And from this, you want to recover your initial image. Okay, so that doesn't look too difficult. The difficulty comes in place when you cannot do a full sweep around the complete body. So you're missing an angle. That's the limited angle computed tomography. And we will see that the mathematical details in a moment. Let me just show you already now what the problem basically is. So this is, let's say, my original image. And then if you're missing this angle, the recovered image always looks like this. So you have this blurry part, this large blurry part in some area, because this is a large angle of missing data, which you don't have a chance to acquire and which is just not possible to, let's say, model in some way. Good, so let's be a bit more specific. So what a CT machine does is it basically computes the radon transform. You will see this formula here. So this is your human body. These are these lines along which you compute the integrals. So you have here this angle, and you have here the offset where you compute, let's say, these line integrals next to each other. So this R is now my K, my operator, which I want to invert. And the problem comes, as I said, if I don't acquire data in this whole angle from minus pi half to pi half, but only in a small area. And applications where this occurs is, for instance, electron tomography. So you see this here. You have this device where you have the probe sitting on the device, and now if you turn it, you cannot turn it 180 degrees, because then you cannot get, let's say, through it anymore. Yeah? So you only turn it in a certain angle. So therefore you are missing a certain angle of data which you want to acquire, which you need to acquire basically to be able to recover the complete image. And so now we already discussed many times this problem of sparse regularization, where we have this data fidelity term and this penalty term. Now the operator is the radon transform. If this is my original data, this is, let's say, what's called filtered back projection, a very, let's say, crude recovery strategy, which, if you have this missing angle, looks just awful. But already also with this sparse regularization with shieldeds, you observe that you have this large part where you have very blurry data. Okay, good. So that's the problem. So now deep learning, we discussed already yesterday. Just to recall that, we already saw these two slides. Yeah, so a deep net is basically, the realization of this is a function of this type. So we have this concatenation of F linear maps and this rectifier an activation function, where typically people take the ReLU, the rectifiable linear unit, this very easy function which is 0 up to 0, and then is x equal to x. X goes to x. And this is how the training goes. Also, again, recalling just from yesterday, we have sample values xi, f of xi of a function which we don't know in the background. We have to choose the architecture of the neural network, where, as we also discussed, it's a lot of experience still right now. We minimize a functional, and say an energy functional, where here we have the function, the realization of the neural network. We want to match it to my f of xi's. I have a loss function, which gives me, in some sense, how I want to measure the error. I have maybe a regularization term, because I might want to ensure sparsity of the weights. If I solve this by, for instance, stochastic gradient descent, I get my my network, which is then hopefully close to f. Okay, good. So this is just briefly what we discussed yesterday. Good. So now deep neural networks and inverse problems. So what do you do? So our operator is now again k. So here, similar to before, we now have, let's say, general terms n training examples. These are not that difficult to produce if we have the forward operator. So because what can we do? Well, we just take some images fi, we apply the forward operator, this gives me gi, and maybe there is also some noise which affects it. So then what I aim to do is I learn a reconstruction operator, which, given my g, recovers my f. And so these parameters which I have here, this I want to learn from the training data, so these are my weights and my biases of the neural network. And so here, this is the training data I have, and it's then also not too difficult to test if I have this forward operator, because this I can just test, I can just produce, let's say, a lot of training data, if I'm not maybe that careful about if I affected by natural noise. So I can evaluate it by just taking, let's say, an fi, computing gi with the forward operator, and then applying my, for instance, neural network, and I hope to get the fi back. Well, okay, so how do people use this in inverse problems? There's a very direct approach, which is you just use anything which actually recovers your initial data, your initial image. For instance, filtered back projection can be also something else. You do that without neural networks. Just use the conventional method. And then this might be affected by noise. and you just use a neural network for denoising afterwards. So that's a very, very ad hoc approach. So very simple. You just invert and then you apply a neural network which denoises the image. So people usually take here a convolutional neural network which somehow then learns maybe the structure of the noise, which this inversion gives you. So that's quite easy. Maybe one of the first things people also did. So that's very easy. What people usually do and which networks they choose, and this is all over inverse problems, is what people call a U-net. A U-net, the U comes from the structure of the neural network. It looks like a U. So it's what's called a convolutional neural network. So this we didn't discuss yesterday, but it has, so what it does is it computes convolutions in these layers. So the intuition here, and again, this is not mathematically founded, is that, so you pass your data through this net, and then you also have these KIP connections. So you pass it through the net. So first, the image is kind of compressed to this part. So intuitively, what the neural net does, it pulls out the essential features, and then it kind of expands it again. And so, it's also allowed to pass some information via these connections. But again, there's no theory which tells you a U-net is the best for inverse problems. Would be nice, but there's not. Okay. Anyhow, so this is what people typically use. Good. So that's now a bit more sophisticated. If you solve this generalized Tikhonov regularization problem, you can, for instance, use ADMM. So these algorithms are iterative algorithms to solve this, and they always have two steps. So it's not, I think, necessary now to look exactly at these two steps, but what is important is that one realizes that if this penalty term is the L1 norm, the first step is approximately a denoising step, and the second step, so the proxy, is kind of solving this Tikhonov regularization. So basically the structure, the algorithmic structure, or the structure of the algorithm to solve this generalized Tikhonov regularization problem consists of, let's say, a denoising step and then a step which solves this Tikhonov regularization problem. And this people now use. So what they do is they replace this denoising step now in this algorithm, if we go back, by a neural network. So they place a neural network in the algorithm, in the iterative solver. That's one approach. The other is maybe even a bit more sophisticated. So there we have this proximal operator. So they replace this by a neural network. So you see it appears twice here. Learn the parameters, and then use this in the iterative solver. So basically, what is done is still the iterative solver is used, but parts of it are replaced by a neural network. So then, also there you still have a bit of, let's say, the classical philosophy, how to solve this. You just replace some parts, somehow maybe the denoising parts, by a neural network. And that also works quite well. And then there are other approaches, for instance, where you, which is called variation neural network, you have this iterative solver. Each iteration of the solver you mimic by one layer of the neural network. And so there are different approaches how to combine this. And so for this limited angle computed tomography problem, maybe the closest what people did so far was to use, again, a U-net on the complete image in the wave-fit domain. But this also suffered from a lot of artifacts. Also, the entire image is processed, so you don't have any knowledge about what you actually get out in the end. And so the question there was whether you can do, let's say, maybe a true hybrid approach. So let me, in the last 15 minutes, explain to you one thing we actually did in that direction. So let's take a closer look at the problem we actually need to solve. If we just acquire data in an angle from -15 to 15 degrees, then the reconstruction looked like this, which looks terrible. So now if you increase it, it becomes better. But what you observe is that some parts are already very well recovered and others are really blurry. So which comes from this missing angle. Yeah, so some boundaries features seem to be already visible at an early stage, others are not. And so the question is how you can phrase this. And so there's a mathematical way to actually phrase this very precisely what's happening. And this is phrased in terms of what's called the wavefront set. So what is the wavefront set? In general terms, so wavefront set are the points on singularities together with the direction in which the singularity occurs. Yeah, so let's say this is my singularity, then the wavefront set would be points on it together with the direction in which it occurs. And so typically this is visualized in this phase space. So where you have here the plane, you have here the angle. So each point here, let's say on the singularity curve, is then mapped to the angle at which it occurs. Yeah, and so I mean this is roughly the mathematical definition. So what you can do local windowing on your function. You look at the Fourier transform, you look at where it actually has rapid decay, in which directions, and this the complement is then the wavefront set. But intuitively, these are the points on the singularities together with the direction in which the singularity occurs. Yeah, so that's roughly what the so-called wavefront set is. So this is this whole area of microlocal analysis, which is, I think extremely useful also in a lot of, let's say, PDE settings. Good. So now in these terms, singularity points together with the direction, you can phrase what you already know. So this is a result by Quinto from 1993, which basically says that, certain points on the singularity can be, now if you compute the radon transform, be detected. And maybe let's just take a look at this image, because then I think it becomes clear what it says. So now if you acquire the data, let's say in this direction, and maybe a bit sweeping. Now, if you acquire it in this direction, certainly these singularities you cannot detect. So there's no way, because you just smear them out. But here, those you can detect, because there, you, let's say, compute these line integrals, and at some point they become 0. So if you're, let's say, the angle you acquire your data is in this direction, you will recover here very precisely the discontinuity curve and also the direction in which it occurs. So that makes sense. These will be invisible in that sense. And so depending on which angle you have, you will know very precisely what you can already recover and what not. Now, what you basically need to do is in this wavefront set image, you are missing a certain part. So basically what you need to do is you need to inpaint the wavefront set. So you need to recover that missing part of the wavefront set of your image. And what I didn't say before, but shearlets are actually able to identify the wavefront set. So the complement of the wavefront set you can phrase in terms of decay of shielded coefficients. So let's say these are your shielded coefficients, so F inner product with the shielded coefficients for those parameters. So again, this is scale, this is orientation, this is position, now in the continuous setting. So these are now continuous parameters. And if these inner products have rapid decay, then this point and this direction does not belong to the wavefront set, otherwise it belongs to it. So the message here from this is that at very fine scales, shields are very precisely able to resolve the wavefront set, and in some sense also highlight where the wavefront set is. So if you do, let's say, a shielded decomposition of an image, you look at the large entries, then these are very close to, let's say, the wavefront set. So they pull out those features of the image. So that's one advantage. And then we will use that also for preparing the neural network in some sense, because there, now in the shielded domain, this wavefront set in some sense comes out and the features are already in some sense prepared. The second thing is that if you look in Fourier domain, we have a visible angle and an invisible angle, and now shearlets, the decomposition of the Fourier domain, is also very much adapted to that. Yeah, I mean, maybe not exactly here, but basically also there we know roughly which shearlet coefficients will be in the visible part and which will belong to the non-visible part. So these are the two advantages of shearlets in this setting. So what we basically do, this is the philosophy, we access the visible part just by sparse regularization, and then for everything what we cannot do, otherwise we use deep learning. Okay, and so this is the algorithm. Okay, so what do we do? It's not that difficult. So we first solve a sparse regularization problem. So with a shearlet transform in here, it's a bit more technical. So we also use some weights because we need to weight the different scales and so on. But roughly, this is sparse regularization with shearlets. What we discussed before, here the radon transform. So there we get images like this, which are blurry here, but the other parts are very well recovered. Then, of this, we do a shearlet decomposition, so we compute the shearlet coefficients of those. Some of these shearlet coefficients will be in the invisible part, so there these will be almost equal to 0. Others are in the visible part, and this will be very reliable and also nearly perfect. And so let me also show you that this is to give you a bit intuition on how it looks like. So if this is the ground truth, very easy, you just have a circle. This is the filtered back projection, the rough solution, very, very bad. This is the sparse regularization solution, which is blurry here. And now if you do the following, you use the sparse regularization solution, compute the shearlet coefficients, the visible shearlet coefficients, so the visible inner products, and you complement it with the invisible ones of the ground truth. So you see everything fits nicely together, so you also bring it back to image domain, and you see it's actually indistinguishable from the original one. So you basically very cleanly, by complementing it with this, fill in this missing part and get a perfect recovery. Yeah, so this tells you that what is now missing is these invisible shearlet coefficients which we need to recover.
I didn't understand that. What are you doing with the invisible ones? This is information you don't have.
That's right. So this is just an illustration. So sorry.
I see.
Yeah. So So what I just want to show here is that these are already perfect.
I see.
The visible ones are already perfect, so the invisible ones you need to take care of.
If you complement the computed ones with the ideal ones, you get a good reproduction.
That's right. Yeah. So this is the ground truth. This is the best you can do. Okay. So so you see, what you need to do is now precisely the invisible shearlet coefficients are those which you cannot recover with the traditional method. So these you now own, and only for those you use a neural network. So now you train it from the visible ones, it should recover the ground truth, the invisible ones of the ground truth in the shearlet domain, because the shearlet domain brings out this the wavefront set which you want to inpaint, and then you just put everything together. So here you have these, which are what we want, and we complement it with what we get here. Sorry, this is actually F.
But Gitta, what is the magic? What is the magic behind the fact that that network can detect what you otherwise don't see?
That's like it is always in deep learning. So we train it on, let's say, real data.
She has data in comparison to a sparse approach that just...
So the magic is, that these structures, so it's like, for instance, the following. So let's assume you have an image.
Maybe it depends on how you train it.
Yeah, sure. Oh, absolutely. So it needs to be trained. It's the same, for instance, if you have, let's say...
So you basically have data that represent the ground truth.
Oh, yeah. So let's assume you have an image like this. Yeah, and so now you cut out this part. And then you use whatever people have done before for inpainting. I mean, PDE-based methods, whatever. What it will always do, it will kind of close this part. And so now if you use, for instance, for this task, a neural network which you trained on natural images, it will actually recover this eye.
If on your
Yeah, so that's in some sense.
If on your database you have a lot of faces and.
Yeah, I mean, it's always certainly, I mean, I'm not saying the neural network that this is perfect. Yeah, I mean, we will see that it also generalizes to some part, but this is exactly, I mean, what I also talked about yesterday. Yeah, so there's no theoretical foundation. We trained on a lot of data. For a lot of data, it actually looks nice. What we are working on also now is somehow to understand how certain the network is in certain areas.
Can I interject? What I see is going on. You can yell at me and say no about it. But if you knew the model class, you could design a dictionary to effectively do the inverse problem.
Yeah.
Here you say there's part of the model class or there's something I don't know, this invisible part. So let's think of that. We have a model class, but we don't know it. So we don't know which dictionary to apply. But neural nets are so universal. If we apply it to a dictionary, any dictionary, it does a pretty good job. It seems to be. That's what's happening. So you apply the neural nets to this invisible part. But you do have data to train.
Absolutely.
Right? So you train it, and now you have your good representation system for the invisible part.
Yeah, exactly.
Even though you don't know the model.
That's right. So our first initial idea was to actually design a prior, and design the prior in a way to mimic possible wavefront sets and how they could be filled in. That kind of also seems feasible. I mean, because wavefront sets always look like something like a candy wrappy structure. But then if you look at real data, these wavefront sets look so complicated that, I mean, to the best of, let's say, our approaches, it was not possible to capture this accurately in a mathematically phrased prior. Yeah? I mean, maybe someone has a better idea. I'm not saying that this is the only possibility. Okay, anyhow, so we used also a unit with a few tweaks. This was the minimization, the functional, according to which we optimize that neural network, which I think from what we saw before is now very natural. So the neural network taking the shielded coefficients of this F star, which we got from sparse regularization, it should match, it should output the shielded coefficients of the ground truth of the invisible part. And so what our, let's say, philosophy in general was to use sparse regularization. So I will show you some numerical results in a moment. Sparse regularization methods as far as they go, and then only, let's say, to use the neural network for only the missing parts which you cannot do otherwise. So we know, in some sense, what the neural network does. It does this 3D in-painting of the wavefront set. We only use the neural network for that, which we, and I think also a lot of other people could not do otherwise. We get a much better performance because we don't use the neural network on the entire image, but only for a part of it. So we get less blurring and so on. This is debatable. I will show you one application where we see that it generalizes. This, whether it's a disadvantage or not, is also debatable. Certainly the whole procedure after training is then dominated by the L1 minimization. I talked about also this at Caltech. There people said, well, I mean, it's not really a disadvantage because sparse regularization, if you just use sparse regularization, you certainly also have this, let's say, complexity. So, I mean, one can debate this. Anyhow, so let me show you some empirical results. This is data from Mayo Clinic. There were 10 patients of each 2,500 slices. We used 9 patients for training, 1 for testing, and there was a 60-degree missing wedge in the data. Then we only trained it on this data. We used it then on other type of data which it hadn't seen before, which was of a different type. So this lotus root data set is just a lotus root which is sliced. People put some metal stuff in it and then put that in a CT. And so there was a 30-degree missing match. Okay. Okay, so that's the ground truth. That's the filtered back projection. So what you see here is always the relative error and then some measure which is much more adapted to the human visual system. So this looks really bad. I mean, it has a lot of blurry effects here. This is TV, a different type of regularization. This is sparse regularization. So you see here, I mean, you have all these blurry parts. I mean, here, this part is not recovered, and also here it looks quite bad. Okay, so now, this is from our South Korean colleagues, the one who had, up to then, let's say, the best approach using neural networks for limited angle computed tomography. So they used the neural net on the entire image. So you see, I mean, it looks a bit better. I mean, it's a bit, let's see, closer here, but here also in this part, it looks still quite bad. And this is what we can do. Yeah, so you see, I mean, it's much better here in this area. Certainly, I mean, it's not optimal everywhere, but also this part is much better recovered. Yeah, so you see, I mean, this. Okay, yeah, so also, I mean, people like in imaging sciences all these metrics, where you have the relative error, the PSNR, you have the self-similarity index, you have a different, let's say, metric. Yeah, so this metric is actually, right now, the closest to the human visual score, and it's also very easy to compute. But in all these metrics, you see, I mean, that with what we did, I mean, we are far below or above, depending on how the metric votes. So in this is better the smaller, these are better the larger than all the other approaches. Yeah, so for instance, we compared it also with first using, as we saw before, this filtered back projection and then using the neural network just for denoising. Good, and so this other data set which the network hadn't seen before and also hadn't been trained on, where you have a lotus root and you put a lot of metal things in it, and then you put it again in the CT. This is again the filtered back projection. This is, yeah, so this is the sparse regularization. It looks better because now it has only a 30-degree missing angle, but still not perfect. I mean, also there are a lot of blurring parts. This is from, again, the South Korean colleagues who used wavelets and on the entire image, the neural net. And so then this is what, again, our approach does. And again, I mean, it has not been trained on that. So, I mean, comparing to what you say, it has just been trained on this other data set. Okay, so what I hope I told you in this lecture was a bit about inverse problems. I think it's a very rich, interesting, exciting area, in particular in imaging sciences. Lots of interesting imaging modalities, inverse problems which come up. One very classical method is sparse regularization with shearlets. These are based on mathematical models, and again, be careful with how you use the word model. Here we know the operator, the forward operator. What we are looking for here is the penalty term, the model for the image which we want to recover. And so for limited angle computed tomography, we saw, I mean, there's just a boundary which where we have problems, let's say, modeling, giving, let's say, such a prior information that we can recover precisely. Then we have the database side, where still, I mean, this is a huge problem, and we talked about it also yesterday. So our philosophy is, in some sense, to use classical methods as far as they go, and then just for the remaining part, use a neural net. And so in the last 1 minute, maybe also let me finish with some advertisement by my own. So if you got excited about deep learning and also theory or mathematics of deep learning, we have a summer school in Berlin for 2 weeks in August. So long list of speakers. There will be lectures about the theory of deep learning, but also how they are used in applications and also, for instance, inverse problems. The deadline is April 8th for applying, and yeah, so you can also talk to me. I'm still here until Sunday, and so there's a webpage where you can apply for that. And so with this, I'd like to conclude, and thank you very much for your attention.
Thank you very much, Gitta. Are there more comments, questions?
I can make some complicated comments.
Yeah.
From an approximation viewpoint.
Yes.
So the general philosophy in approximation is you have a model class, and you're interested, well, how well can I approximate the functions in this model class? And there's some, let's say, with methods that depend on n parameters, you can approximate with accuracy n to the minus r. Okay? We sort of think that the r is connected to the entropy of this class. That's not precise. In some cases, it can be made precise if you put some restrictions on the approximation scheme. Now we go to neural nets. And it seems, so you say, well, you could look at it backwards. You could say, okay, I have my approximation method. Let's look at all functions captured with accuracy n to the minus r. That's my model class now. So we're searching what is this model class for neural nets. But if we assume that this model, I mean, if we have that the entropy of this model class is n to the minus r, this is what is puzzling me. How it's restricted, so that the objects that the neural net can capture is still restricted, that it has to be a set with entropy n to the minus r, entropy numbers like n to the minus r. So you sort of think, well, it's sort of universal. I can, whatever wavelets can do, neural nets can do. Whatever shearless can do, neural nets. When it's doing every possible method, it can find a dictionary inside the neural nets that sort of do whatever particular thing does. But if I take the union of all those approximation classes, wouldn't I have something with entropy not n to the minus r?
I think you would, but I also think the situation is a little more complicated, because when you say the wavelets can do with n to the minus r, and then maybe tensors can do with n to the minus
different
r.
model classes, right?
Different model classes, and these nets seem to be universal, that they can do it for all of them simultaneously. But you are already mixing up different scenarios. The wavelets get for a given r, get this n to the minus r, maybe for functions of 3 variables for a reasonable r. While the tensors can get that n to the minus r for a function of many, many, many more variables. And the neural networks are not the same for those two, because the input layer would be actually, each time would be different. So I think it's just more complicated to taking the union of all these possible sets, because in one scenario you have functions of 3 variables, in another scenario you have functions of
no, but let's fix the number of variables we have.
Yeah.
We're trying to capture functions, certain functions, mapping Rk into Rm or whatever.
Yeah. But then if you bring the wavelets into the game, and that would be extremely smooth fun. And if you say functions of 100 variables and you bring the wavelets into the game, then this addition would be a very, very thin set, because it would require very high regularity to get that n to the minus r. That's a problem. Okay, maybe we can.
I mean, nothing can be so great that it can do everything.
That's right.
Yeah.
That's
So
right.
there has to be limitations here.
That's
What
right.
are the limitations? Why does it? I mean, we always knew that we could create bigger and bigger dictionaries, but we didn't know how to look inside the dictionary and find what is the representation. I mean, the bigger the dictionary you have, the harder it is to do your optimization problem, right?
I mean,
This is a very big dictionary, neural net.
very big. Yes.
Maybe this is one of the drawbacks is that we don't understand whether these optimization techniques really extract from the dictionary the right system. They seem to
Sometimes, yeah.
sometimes.
Well, it depends also sensitively on the starting value and so on. I mean, training these neural networks is not an easy task.
It would be, I mean, you know, from a philosophical point of view, are you willing to take, let's say, in the medical imaging, you can't prove that what you have obtained is with any fidelity
Yeah.
accurate. And so suppose you say somebody has cancer based on this, and they don't have cancer, you're going to go to the court, and the lawyer is going to rip you apart if you apply something that you don't even know whether it works or not.
Yeah. Yeah, so therefore I say, I mean, I think I also said it yesterday, I mean, for sensitive applications, these neural networks are, yeah, to some extent not ready yet. So there's a lot of theoretical foundation which is still missing. I mean, even what I think here, what one wants like to know is, for instance, if you have, let's say, a reconstructed image, how certain is the network in, let's say, certain areas of the, like an uncertainty map or something like this.
Didn't this Google driving car have an accident or something, right?
Yeah, yeah.
So,
Sure, that's right. I mean, even for instance, I mean, if you also, I mean, in the end, I guess it's also used for maybe military applications and so on. I mean, it will go in a lot of different areas.
Collateral damage.
Collateral
Collateral damages.
We'll bomb Bulgaria instead of Romania.
Yeah, so therefore I think it's for mathematicians, I mean, a very, let's say, essential task also right now to provide a more theoretical foundation for that and put it on, let's say, stable feet. I think you also had a question. Or?
Yeah, actually one question was just asked when questions were like about like how I was concerned about like more instead of false positives, like false negatives, like you're injecting a lot of bias towards prior knowledge, and like maybe we are looking for exceptions in imaging, and yeah, that's, I mean, how can we handle this risk somehow in this scenario?
I mean, this scenario, so to some extent, I mean, as I said, it's a combination. So the reconstructed image is a combination of, yeah, it's a reconstruction of something where you have error bounds and so on. And here you know what you're dealing with, and this other part. So you can identify to some extent in your image which parts are safe and which parts come from the neural net. But I mean, those which come from the neural net, I cannot say much about that. Huh? So there's no certainty. I mean, there's also not something that you can say, I mean, this tumor is, I mean, it's more likely that you have a false positive than a false negative.
So this
that's the problem.
idea of using existing technology on the first part and then neural nets on what remains, is that your idea or was it some?
Yeah, so that was, I think, yeah, so I mean, okay, so there was a long list of authors, but yeah, so maybe, yeah, so this is actually my PhD student, Maximilian Merth, and then there are colleagues from the Fraunhofer in Berlin, and also colleagues from Helsinki.
So rather than apply neural nets at the beginning, you say, I apply something I know very well, and I know how well it does, and then I'll apply neural nets on what remains. So if neural nets screw up, they're really screwing up on that.
Yeah.
Just one part.
Yeah, I mean, I cannot, I mean, I don't know, let's say there's a huge literature using neural networks for applications. I mean, it could be that in some of those maybe there is maybe something similar. That I cannot say, but I mean, to the best of my knowledge, I mean, this general approach was the first.
Just philosophically, isn't it better to to hide from neural networks some things you think you know what it is, and then just check after that whether it will recover it well.
To hide from neural networks? How do you mean? I mean, so you need to train them on something.
Okay.
Yeah, he's going to make a training set where he actually knows what's...
Yeah, but I mean, that we did in some sense. This lotus root, the neural network, I mean, these types of data, the neural network never saw. So so something like this, the network never saw. So that's what people then call generalization, to some extent.
Yeah, I get that something.
Okay.
Would it be possible to take an image that is already sort of very clear that you wouldn't necessarily need to actually apply anything to, but just for the purpose of testing whether how well your system, your model generalizes, apply some sort of random noising function that would blur the picture somewhat, in a similar sense, and then test your own model on these images and test how it compares to the original picture?
So you would like to take just images? I mean, so here the main point is to fill in this missing wedge.
Yeah.
So you want to take images, you want to pull out the wedge?
Yes.
Yeah, but I mean, this is in some sense what we do here. Because, you see, I mean, the data, yeah, so this is the ground truth. It is the data without any missing wedge.
Yeah.
So we can test how good it does on that.
But
So maybe I didn't understand you.
So what I'm sort of asking is, it seems like you got most of your information from fairly small data, well, not small data sets, but you had what, did you say 10 patients?
Yeah,
So
each 2,500 slices, yeah.
yeah.
But then, I mean, you also, you also do some data, what people call data augmentation. Yeah, so you have your training data, and then you also shear it and rotate it to create more training data for your net. Yeah, so that's in a way a very natural procedure what people do. And also in life sciences, that's actually always the main problem, to have training data, because I mean the clinics are very, let's say, cautious to give that out. So this was here a challenge, where this Mayo clinic gave that data for free. But otherwise, it's usually a huge problem to get to such data. That's the main problem in this area.
I mean, this reconstruction certainly look very good. This one. You mentioned these other approaches, just as what people are doing. And when they just replace, say, we have seen now when they just use the neural network as a black box on the whole task, it is not as good as what you do, clearly not as good. But these other things, like replacing the approximate in the iteration, did that show any real advantage? Or did people just do it because they wanted to do something with neural network? I mean, was there any incentive for doing
What should I say? I mean,
any other incentive? Did it show good results?
Yeah,
in
I don't think.
Better?
Yeah, I don't think anyone did that only to have a paper on neural networks. I mean, that I would actually not. I don't think so. I mean, usually in these papers, I mean, there's one application where people show that it has some advantages with respect to conventional methods. So because otherwise, I mean, why would you do that?
I mean,
But
in your case, when the L1 norm say is well, these proximates are not so hard to evaluate.
yeah, but I mean, the problem is, I mean, if you do what I said before, I mean, then basically you change the entire image. Yeah, so then, I mean, your network will affect the entire image each time. Yeah, so here, I mean, if you use these approaches, you always change everything. Whereas for us, I mean, that was our philosophy there, and there was already mentioning about this, let's say, delicacy of clinical data and clinical applications. There, at least, for a large part, you have certainty of what you do. And you just use for that part in your network. Here, in these approaches, whatever your reconstructed image is, you don't have certainty about any part of the image. So that's...
Yeah, no, I see that. I was just wondering, what was the reason for people doing this?
Oh, I mean, each time, I mean, each of these papers has a particular interesting
Cases
application.
where-
Yeah. So it always showed its benefits.
I see. well, I think we are.
Do we get coffee or what?
I think we have a
If it
Huh?